Hello, this is a video designed for students who are anxious about their first exam B, their first in-person exam in Chemistry 151 at the University of Arizona. So what I want to do is give you some information about what it's going to be like and how you should, in my opinion, recommend prepare. All right, so exam 1B is a multiple choice exam, about 15 questions, and a free response exam. So it's a hybrid exam of both of them. Each multiple choice is worth about 4 points. The free response, there's about 6 of them, and the answers are graded for accuracy. Each question must be justified for credit. Right, so that's really important. Exam 1B is going to be 7% of your total grade. And the most important aspect of exam 1B is learning what it takes to prepare for all of the other exams, right? So you may mishandle exam 1B, or there might be some missed opportunities, but there can't be missed opportunities for learning. And the first thing I recommend to students always is look at the entire exam before you start answering questions. Pick and choose your battles. Go through it. Do you want to start free response first? Do you want to start multiple choice first? It really is up to you. But there's no prize for going question by question. So no prize for going question 1 through question 20. Okay, no prize. Okay, so what we're going to do now is... Okay, I didn't realize this was going to be on here, so let me erase this. Thank you. So multiple choice questions look like this, and you'll see many examples of them in our practice and our activities, because you could imagine here a picture, and this was on a previous exam, and what we had was, A, B, C, and D, right? Each question. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 8. So you have an image and you're going to be asked some questions about it. And each one will be A, B, C, or D, and you get to pick from it. I'm going to go over the answers to this question a little bit later in the video, but the main thing is I just want to make sure it's clear that when you look at these reviews, the multiple choice will look like this. Very specific. Here's an image. What's the answer? How many substances? What's the answer? How many compounds? What's the answer? Okay. So this particular review that we're going to cover is about carbon-hydrogen containing molecules. Okay. So this is what a free response looks like. Right, so this is free response. And you know it's free response clearly because you see the word justify. Okay, so a really good idea to sort of sketch your answer for free response questions. They're going to look like big blanks here. You're like, what am I going to write here? Well, you write what the answer is, right? That basically. So what you need to do is go, what is this question asking, right? That's number one thing. What is this question asking? Well, they want a Peck diagram. We already have the axes, so we don't have to provide that. And then, for this, we know there's different quadrants, right? There's high config, more random, low potential energy, closer particles. Right, so these are the key that, randomness and proximity, right? We could think of this as the proximity axes. And now we have trapped in rocks, right? So you could say, okay, trapped in rocks, so that's MT. So we have little CH4s, and they're sort of trapped in rocks, right? Close together, ordered. And then we have released, which is all the rocks are over here, and CH4 is now free, random, Okay, so now we kind of see that. Oh, okay, so far apart is MR is far apart. And MR is more random. So we have two states here. It looks like this. The trapped are closer particles. The trapped are ordered. And so now we have our justification, right? We say, okay, so MT has lower potential energy because rock and CH4 particles are closer, which is a lower potential energy because they attract. So there's our potential energy argument. The configuration argument, right, would look like, okay, well, the trapped, cannot move, less random, less configurations. Right, so that's how we would expect you to build this argument to justify it. Justification requires that you put answers inside the particulate, right? The particulate model of matter. Right? You have to have these answers, right? Particles are closer, the randomness, configurations, these are all aspects of the particulate model of matter. Okay, so now that we have this, what would happen if we were to change the temperature, change the pressure? Okay, so what we would know is that MR, so more MR if the pressure is lower, but the T is higher, right? And you say, why is that? And that has to do with its high potential energy and low configurations. Right, so those would be the answers that we would be looking for in this type of problem, is building your PEC diagram, justifying it based on some aspect of the problem. Here we're told that these are trapped and close together, so that lowers the potential energy because there's attraction, right? The attraction, the closer they are, the lower the potential energy. Okay, but what you do see are two different independent arguments, one for potential energy and one for configurations. All right, so if we wanted to release MR, release the CH4, we would want to do this at the low pressure, high temperature region. All right, so here's our multiple choice problem, and you could imagine these being like I said, A, B, C, D, and these were answered before, but we kind of this is the first one is a submicroscopic. So two phases, gases are far apart, high potential energy, liquids are close together, low potential energy. Okay, how many different substances are here? Looks like 3. There's the blue guys. There's small, black and white, big, black and white. How many different chemical compounds are there in the gas phase? It looks like there's 2. How many elementary substances? Remember, there's one type of atom. So that's N2. In which phase are the particles moving at a higher speed? So this is like lowest mass. Lowest mass here is, N2 equals 28. C3H8 is 3 times 12 plus 8, which is 36. So this is 44. C4H10 is 4 times 12 plus 10, 58. So this is the fastest. This is the slowest. highest mass. Okay, in which phase do they have the lowest potential energy? Well, we answered that already. Same, right? All kinetic energy, right? All kinetic energy is the same if they're at the same temperature. How many substances would we have in the system if all of the LPG is, this mixture is boiled and transformed into vapor? And that would be 3, right? The total that we have. So this is what you're expected to do, analyze phases, elementary substances, chemical compounds, potential energy, and kinetic energy. Right, another free response. How would you explain using this particulate model of matter? Okay, so particulate model of matter, 1, lots of little particles. And they're identical in a pure substance. Okay, so that's the first rule. 2, moving in a distribution, some fast, some slow, at which is with a kinetic energy that is proportional to temperature. And this is mass v squared is proportional to temperature. So that's our second assumption. And third, all particles attract. All particles attract. Stronger requires more energy to separate. And in general are closer. Okay, so these are our 3 aspects of the particulate model of matter. Now we just say, okay, which one of these? So this image shows the time it took for substances to go through a chromatographic column. Ethane exits first. So what we're saying is we have this column, and our molecules, our ethane molecules, kind of go through. And if they attract to here, they spend more time. We call that slower. So they spend more time there, and I will say they spent, in the exam, they spent more time telling you about this. We just kind of cut this out of the test. But what it does say is that we have to use 3 and just say, okay, ethane attracts less, so it goes faster through the column. So we definitely would want to use number 3. We'd want to use the third assumption here because we're talking about time going through the column, a particular substance. That's important. Also, on average, is ethane the lightest, right? The lowest mass. So then it's going faster, going fastest. Right, so in this case, it's going faster through the, and this makes sense. This is using number 2, right? So number 2 is the faster particle goes through the column. The lowest mass goes through fastest. And if that's the case, then ethane would go through, and then you had the masses here. So the so lowest, highest. And I'm going to say this is probably the most popular answer that received credit. So even though any speed of a molecule goes through a distribution, and we've talked about that, number of particles, that has a distribution, That allows, so some are going really fast. The average speed, right? The average speed, this is for ethane. And then what we'd say, if something was heavier, then it would just kind of look like that. It would go slower. So it's all we knew. So we didn't know anything about the column, right? Because that was in the test, but it's not here. Let's say we ignore this one because we don't have enough information to say this based on what we're given. But what we would say is number 2 is going to be helping us here because the lowest mass, which we do have, and you'll be given the formulas of this, the faster it is, the faster it goes through this column. With the lower the mass, the faster those particles are. All right, so here's a calculation problem that we did in class. So water result 0.023 grams. So we have 0.023 grams of CH4. And what we want to know is how many molecules. Okay, so this is done in 2 parts. We go grams to moles. Okay, so we just take this unit, put it down here. We know what we want. So 1 mole is 12 plus 4, 16. And then we go to molecules. So we need molecules in the above. And there's 6 times 10 to the 23rd for every 1 mole. Remember, whatever this unit is goes to the bottom. And then we get the answer. And the answer here is 0.023 divided by 16. So it should be a lot of them. 8.6. Okay, so there's another way to do this problem. You say, remember, we don't really care about the liters, so we're not even using that. Another way to do this is to say x grams equals y moles equals z particles. And then what we do is we just divide by we would just fill this out. Y moles, 1 mole. So this kind of helps us because what we can do here is say given x in this problem, we'll find z. Ooh, okay, so given x, find z, so we're just using this and we're using that. So we just say, okay, we're given x as 0.23 grams. And we know the molecular mass here is 16 grams per mole. And we want to find z. We don't know how many particles there are. And we get 6.02 times 10 to the 23rd. We solve for z, and we get 8.6 times 10 to the 20. So this is a really good way to do the problem too. Kind of depends on different ways that you think about the math. But the molar mass is 1 mole. And it's 6.02 times 10 to the 23rd. So all you have to do is, if you're given x, you can find z. Given z, you can find x, if you remember this formula. But either way, you get the same answer. All right, so building delta E versus P, delta E versus T, different graphs are going to be really important in this. So let's take a look. So we have 1. So you go to 15 degrees Celsius plus 273. Right, so 288 Kelvin. We'll call this 290. And so we start here at 1. And then we go up to 2.5. We'll go through a phase change. All right, so when we build delta E here, what we need to know is this is plus and this is minus. Plus means increasing. And this means decreasing. So what does that mean? Remember, our model looks like this. Here's our ladder at 0. So when we talk about increasing, right, this is potential energy. So if we're going up, you know, because this is liquid, gas, right, solid. So if we're going gas to liquid, we're going down, and this is decreasing. So we're going to be down here. Here's pressure. So if we have 1 here and 2.5 here, initially there's no change, right? Initially there's no change, but we have to go negative. So as we reduce the pressure, right, so we're going down, there's really no change, no change, no change until about, so this is 1, 2.5, this is about, I don't know, 2. And then there's a big change down, and then there's no change, no change, no change. So it looks something like that, right? Decreasing as we start in the gas phase at 1 atm, and then get to the liquid at 2.5. But we make the change though at 2. So at 2 we go down through the phase change, and it's negative. If we were going to do the same problem, let's say 1 atm, and we do the temperature at 200 Kelvin to 300 Kelvin, then what we would see is, okay, so do delta E plus and minus, and then so we're doing temperature now, and if that's the case, so we do 200 here, so I'm just going to make up a new problem, and we're going to go this way. So we're starting at the liquid, so in this case, solid, liquid, gas, and then I'll just change the marker, pen marker. So now we're going up. That's a change in energy that's positive, right? And that's up in energy. Delta E down, negative. Okay, so what does that do for us? Well, that allows us to now, remember, we always start at delta E equals 0, right? So delta E equals 0 is always the start. Here we started at 1 atm, so the delta E is 0. Here we're starting at 200 Kelvin, right? 200 Kelvin. And now we kind of do the same thing. We have the phase change is at 260. So we have a change in kinetic of the liquid, a step up, and then a change in kinetic energy of the gas. So there's our phase change there, and now it's positive, right? It's positive because kinetic energy is going up, 200 to 260, 260 to 300, and the potential energy is only going up at 260 as we go to liquid to gas, right? So these are the kind of arguments justifying your reasoning, explaining, showing the energy diagram, talking about potential energy, and in this case, it was just total energy, but you can kind of get a sense of what we would be asking. Okay, so here's the question. Estimate the minimum pressure needed to liquefy, right? To liquefy butane. So what does that mean? That means you're starting at a gas and you're going to a liquid. So at 15 degrees Celsius, so then 15 was 288, right? So we're here. And so we kind of go up here, gas, 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 increasing the pressure, and then it's about 2 atm. 2 atm needed to condense butane. Right? To condense butane. Describe how the average kinetic energy and potential energy of butane molecules change during this process. So we'll just say, what is this? Pressure. So this is pressure going from 1 to 2.5 atm. So that's like the same problem at 15 degrees Celsius. All right, so over here, do the phase change at 2, then up to here. Okay, so how does delta, so delta kinetic energy overall goes down. Why? Because we're going gas to liquid for the reasons we talked about. So delta kinetic energy is 0 because there's no change in temperature. So if temperature does not change, then kinetic energy does not change. And now we have the change in potential energy. Whoops, potential energy. Well, we're just using our ladder here, solid, liquid, gas. Starting at gas, remember gas to liquid, solid, down, so it is decreasing. Particles, attracting particles, right? Attracting particles are getting closer. EPD goes down. So attracting particles are going down. All right, so now we're going to go into some vapor pressure curve problems. So here we have lowest boiling point. Actually, this is highest. I said it right before. Lowest boiling point, highest boiling point, weakest attractions, highest or strongest attractions. All right, so volatile. So what does that mean? That means that if we have like a mixture here, let's call that T equals minus 180 degrees, right? So they're all sort of liquids. You have M, E, P, M, E, B, B, M, E, B, M. Right, so let's say you have, so here's your liquid. And what does volatility mean? Is that there's more M any given temperature, then you're going to have a couple E's and then one P, right? So that's what volatility means. Volatility means is the number of particles, number of gas particles at any given temperature. Right? Because remember, there's always a distribution. So this might be the boiling point energy. So only a few, right? Only a fraction of the particles have enough to boil off. This is below, right? So this is going to be all liquid. And so that's what they mean. So the boiling point energy, so if this is stronger, it goes that way, there's less particles in the gas phase. And if that goes this way, meaning it's weaker, there's more particles in the gas phase, right? So at any given temperature, right, remember this is number of particles. At any given T number of particles. So that's really what we're talking about in terms of the distributions. So that's what we could see. Okay, so M is weaker. There's definitely going to be more M. So methane, remember this was M, E, and P here. So methane is going to be more volatile, more particles in the gas phase at any given temperature. All right, in which substances do particles have the strongest active interactions? What is going to be the highest boiling point? Because more energy needed. to separate liquid into gas phase. And in which substance to particles have the highest potential energy in the liquid? This is going to be the lowest boiling point, which is going to be methane. That's going to be that one was propane. So if we had to rank the potential energies here, remember the gases, so M gas, E gas, and P gas, they're all at 0 potential energy. And then the liquids are look like this: M liquid, E liquid, P liquid, strongest. Whoops. So this is the weakest, strongest interactions, lowest boiling point, highest. And we know that because the distance between the liquid and here. So these are the kind of arguments that we'd expect you to make. What is volatility? How do particles get into the gas phase? Well, they get into the gas phase below the boiling point because of these distributions. The weaker the interaction, the more particles are in the gas phase. All right, so let's do a vapor pressure curve. All right, so vapor pressure versus temperature. We're going to have 3 substances. They're going to look like this. These are all at 1 atm, so we'll just put 1 atm here. And we're just going to call this one minus 161, this one minus 89, this one minus 42. Right, so the highest boiling point, remember, if we were to put these in Kelvin, then this would be 90 Kelvin, this would be 200, nope, this would be 180 Kelvin, and this would be 230 Kelvin, right? So 90 Kelvin. So it's often easier to think about this in Kelvin because it's easier to see the progression here with these minus signs. It's a little stranger. And also we could just rank the potential energies that way. Minus 90 for M, minus 180 for E, and minus 230 for P. Right, a little bit easier to see the potential energy ordering if you do our hack where you just take the minus of the boiling point temperature. Right, so it would look like this. And then what else? Justify your reasoning. Well, I guess it's just going to be the lowest boiling point. Highest boiling point. All right, so took a while to get through it, but the key, you can see the kind of problems you're going to have to do. Free response. Make sure you know the particulate model of matter, right? Particulate model of matter. We already said it. Number 1, lots of little particles. Of little, identical particles for a given substance. 2, always moving in a distribution. And that has a bunch of kinetic energy is proportional to temperature, which is equal to proportional to 1/2 mv squared. Mass goes up, velocity goes down. Some particles can leave the liquid due to the distribution, right? Due to the distribution. Weaker attractions. More particles in the gas phase. More particles leave. Okay. That's the story, and we've talked about it several times. If this is the number of particles that leave, this is for a strong, for a velocity, right? Number of particles can leave for a strong. If they're weaker, look at how many more particles can leave. Woo! So that would be, so this would be weaker attractions. And now look at how many can leave. And so that puts more particles in the gas phase. 3, all particles attract. And it's stored, right? Stored in potential energy. So if you kind of think of these arguments and then the other, so you can kind of think of that in terms of free response. These are the kind of arguments you're going to need to make for the free response. Temperature only changes when, kinetic energy only changes when temperature changes. The other is particle potential energy only changes with phase change. And we talked about that with our model: gas, liquid, solid, potential energy. All right, so we kind of keep that in mind. This is what you're going to have to navigate. This is what you're going to need to be able to do. Then when you go through our practice exam, the other practice exam that's on D2L, or our reviews that are for extra credit, and you'll get a sense of exactly what we're going to ask you to do. Remember, what all the questions have in common, what all these activities have in common, is what we're most likely going to ask you. Okay, good luck.